It's mysterious and wondrous. Welcome to the world of relativity. In the theory of special relativity, there are several classic paradoxes. Understanding these paradoxes can help us gain a deeper insight into the properties of spacetime and revise our traditional understanding of the fundamental laws of the universe. The faster-than-light paradox. In Alice's reference frame, Bob moves to the right at 0.6 times the speed of light, and Charlie moves to the left at the same speed. One might naturally assume that Bob is moving relative to Charlie at 1.2 times the speed of light. Is this statement accurate? Does this imply the existence of superluminal speeds? In fact, this description has some issues. When we generally talk about Bob's speed relative to Charlie, we are referring to Bob's speed in Charlie's reference frame. However, what we actually want to express is the rate at which the distance between Bob and Charlie increases in Alice's reference frame. Therefore, a more rigorous statement should be, in Alice's reference frame, the distance between Bob and Charlie increases at 1.2 times the speed of light. The non-existence of superluminal speeds refers to the fact that in any inertial reference frame, the speed of any object cannot exceed the speed of light, not the impossibility of the rate of increase of a certain quantity exceeding the speed of light. So if we switch to Charlie's reference frame, would Bob appear to move relative to Charlie at 1.2 times the speed of light? The answer is no. By applying the Lorentz transformation to shift the spacetime coordinates to Charlie's reference frame, we discover that Bob's speed in Charlie's frame is not 1.2 times the speed of light, but rather 0.88 times the speed of light. This result tells us that in any reference frame, the speed of any moving object cannot exceed the speed of light. We will explore in detail in future videos how this value of 0.88 is calculated. Understanding the following points will clarify the faster-than-light paradox for everyone. First, when discussing speed, it is essential to specify the reference frame. Any speed without a reference frame is nonsense. Second, within a given reference frame, the speed of any object cannot exceed the speed of light. Third, within a given reference frame, the distance between two moving objects can increase at a rate exceeding the speed of light. The twin paradox is one of the most famous paradoxes in special relativity, arising from the effect of time dilation. Let's consider a pair of twins, traditionally named Alice and Bob. Alice stays on Earth, while Bob travels away from Earth at a very high speed, then returns at the same speed after some time. In Alice's reference frame, draw Bob's world line. Mark the points of Bob's departure, turnaround, and return. Point P is the midpoint of the time from Bob's departure to his return in Alice's reference frame. Events P and Q are simultaneous in Alice's reference frame. Due to time dilation, Alice perceives Bob's clock to be slower. Therefore, although the time coordinate of point Q is L in Alice's reference frame, in Bob's frame, it is L multiplied by a number less than 1. This represents the time experienced by Bob between events O and Q. Again, the journey from Q to T, just like the journey from O to Q, only differs in the direction of motion. Time dilation effects do not change with the direction of motion. Thus, the time experienced by Bob on the journey from Q to T is the same as that experienced on the journey from O to Q. From the analysis above, when Alice and Bob reunite, the time elapsed for Alice will be longer than that for Bob, meaning Alice will be older than Bob. If Bob's speed is sufficiently high, Alice might be elderly, while Bob remains youthful. However, when we consider this problem from another perspective, the oddity becomes apparent. From Bob's viewpoint, he remains stationary, and it is Earth and Alice that move away and then return at speed v. Using the same analysis, we should also conclude that Bob would be older than Alice. This is the twin paradox. To understand this problem, we need to switch to Bob's reference frame and see what really happens. We start by switching to the reference frame of the first half of Bob's journey. In this reference frame, the event simultaneous with point Q is no longer P, but point P1. This is also why Alice and Bob each think the other's clock is slowing down. They are actually comparing different simultaneous points. We then switch to the reference frame of the second half of Bob's journey. In this frame, Bob's second half of the journey remains vertical, indicating he is stationary in this reference frame. In this reference frame, the event simultaneous with Q is no longer P, nor P1, but P2. At Bob's turnaround point, he undergoes a brief but intense acceleration. During this process, Bob perceives Alice's clock to speed up dramatically, moving quickly from point P1 to P2. This explains the twin paradox. The motion of Alice and Bob appears symmetrical, but it is not. Alice remains in a single inertial frame, whereas Bob's journey is split into different inertial frames, and he experiences a dramatic change in velocity at the turnaround point. It is precisely because of this intense acceleration that even in Bob's reference frame, when he reunites with Alice, he is younger than her. This conclusion is consistent with the analysis in Alice's reference frame. The pole barn paradox. Imagine a barn and a pole. When stationary, the pole is longer than the barn, making it impossible to fit horizontally inside the barn. The barnkeeper, familiar with special relativity, devises a plan. By moving the pole at a very high speed, its length contracts, allowing it to fit inside the barn. However, the pole's owner, after studying special relativity, disagrees. From the perspective of the pole, it is the barn that is moving at high speed, causing the barn's length to contract. Since the pole couldn't fit before, the barn's contraction makes it even less likely to fit. Which perspective is correct, the barnkeeper's or the pole's owner's? We need to consult space-time diagrams for the answer. Consider a reference frame where the barn is stationary. Here, the moving pole experiences length contraction, making it shorter than when at rest. The pole moves to the right until it is fully inside the barn. We mark the space-time points of the barn's front and back doors at events P and Q. Applying the Lorentz transformation to switch to the pole's reference frame, our initial impression is that P and Q are no longer simultaneous. In this frame, the pole remains its original length, while the barn appears shortened due to its high speed. When the time reaches the moment of event Q, the front end of the pole is deep inside the barn, but the rear end is still outside. When the time reaches the moment of event P, the front end of the pole has already moved out of the barn, while the rear end has just entered. This is the true essence of the pole barn paradox. The barnkeeper believes that at some point, both ends of the pole are simultaneously inside the barn. The pole's owner disagrees that these events occur at the same moment. From their respective reference frames, both are correct, yet their statements are not precise. Thus, when confronted with space-time conundrums, clarifying the reference frame and analyzing with space-time diagrams can often help us untangle issues and uncover the truth.